equations and stuff like that. We talked about the steps, and again, reminder that you do want to make sure when it's all said and done that those two things that we talked about is done. You have all here. So again, I'm just going to make a table like I did before, reactant product, and make sure and count up everybody on each side. On the left-hand side, we have 1 nitrogen. Right-hand side, we have 2. Left-hand side, we have 1 oxygen. Right-hand side, we have 1 as well. And left-hand side, 2 hydrogens, and also 2 on the right-hand side. So this one is pretty much balanced except for the nitrogen. So again, that's a pretty good place to start. We will put a coefficient of 2 in front of it on the left-hand side. That is going to give us 2 nitrogens. That will now also multiply that in, give us 2 oxygens, and we will still stay with 2 hydrogens. Again, much like what happens, we kind of fix one thing, screw up something else. So that will then take us to oxygen as a good thing to fix. We'll put a 2 in front of the oxygen on the right-hand side. That's going to give us 2 nitrogens, 2 oxygens, and 2 times 2 is 4 for our hydrogens. At this point, we can now clearly see we just need to go back to the left-hand side there and put a 2 in front of the H2. And that will give us 2 nitrogens, 2 oxygens, and 2 times 2 there is 4 hydrogens in that case. Any questions on that one there? Come. All right, then let's do this one next. Okay, so doing our little table here, we got 3 carbons on the left, 1 on the right. We got 8 hydrogen on the left, 2 on the right, 2 oxygen on the left, and then once again we got oxygen in a couple places here, so we have 3 total there on the right-hand side. Once again, the easiest thing kind of fix first would be carbon, perhaps. So we could put a 3 in front of it. That's going to give us 3 carbons. We will still have 2 hydrogens. Our oxygens now get to 7 with 6 in the first one and 1 more on the second, which is 7. Once again, the next easiest thing to really fix is the hydrogen, and we can do that by putting a 4 there in front of the hydrogen on the right-hand side. That gives us 3 carbons. 4 times 2 is 8 hydrogens. Our oxygens now get to 6 there, and 4 more there is 10. And that makes it pretty simple to fix the oxygen on the left-hand side by putting a 5 in front of it. Gives us 3 carbons, 8 hydrogens, and now 10 oxygens. So we are good and balanced. Any questions on that particular one there? All right, so give this one a go, right, and then balance the equation. Diboron trioxide reacts with water. Okay, let's take a look. So obviously we have everything in words. So we want to first, as we talked about, make sure we do get everything correct formulas. So diboron trioxide is a type 3, so that should be like a B2O3. Reacts with water, which is H2O, to form boric acid, which is this guy here. Now that I have all the correct formulas down, we are good to balance at this point. So we got a little boron, oxygen, hydrogen. Left-hand side, 2 borons. Right-hand side, 1. Left-hand side, 4 oxygens. Right-hand side, we do need to multiply the 3 in. So that's going to give us 3 oxygens. Left-hand side, 2 hydrogens. Also, we'll multiply the 3 in here and give us 3. Not a lot to work with here, so might as well start with the boron. We could fix that by putting a 2 on the right-hand side. That gives us 2 borons. For oxygen, we do multiply the 3 in, but then we also need to multiply the 2 on the outside. That gives us 6. Same deal there for the hydrogen, multiplying the 3 in, and then also multiplied by the 2 gives us 6 of those hydrogens. At this point, we can fix the hydrogen, probably the easiest since it's in only one place over here on the left. And we can do that by putting a 3 in front of it. Gives us 2 borons on the left. 3 times 2 is 6 hydrogens. And our oxygens is 3 and 3, which is 6. So that fixed, obviously, the oxygens as well in this particular case. Any questions on that one there? All right, one last one here. Balance this guy up. All right, so once again here, we do a little table. We got one nitrogen on the left, one on the right. We got 3 hydrogens on the left, 2 on the right, 2 oxygens on the left, and we also have 2 on the right, 1 in each of those guys. So everything's balanced here except for hydrogen. In this case, we actually need to put numbers on both sides. 6 would get us sort of a balanced hydrogen on both sides. To get our hydrogen on the left to 6, we need a 2 in front of it. To get our guy to 6 on the right there, we do need a 3 in front of it. That's going to give us 2 nitrogens, 6 hydrogens, and 2 oxygens on the left. 1 nitrogen, 6 hydrogens, and 4 oxygens at this point. 1 in the first one, 3 in the second. Next easiest thing, again, to balance this oxygens in a few different places would be the nitrogen. So we could put a 2 in front of the nitrogen on the right, giving us 2 nitrogens, still 6 hydrogens. And in this case, we have 2 oxygens on the first one and 3 in the second one, which would be 5. Once again, at this time, it's pretty much all we got left is oxygen. We need to basically turn our 2 into a 5. So this is a fraction situation, which would be a good way to do it. Once again, the fraction is pretty simple. Up on top is the number you need. So in this case, we need 5. And on the bottom should always match this number, which is a 2. And if we do that, that would give us 2 nitrogens, 6 hydrogens. And again, when you take 5 halves times 2, you will end up with 5. And that would give us our balanced equation, except obviously, once again, here we do have a fraction that we do need to clear. So we're going to multiply the entire thing by the denominator, which is 2. And that would give us 4 of the NH3 plus 5 O2, 4 NO, and 6 H2O here. And once again, we should still be balanced. We got 4 nitrogens on each side. We got 12 hydrogens on each side. And we have, in terms of oxygen, 10 on each side. 10 over there, 4 and 6 here gives us 10 oxygens. Any questions on balancing the equations here? Okay. So clearly you need to be able to write equations, balance equations properly. One last thing here in terms of equations. Sometimes you do get some equations that do have some polyatomic ions in it, and you definitely could go kind of element by element like we did previously. But sometimes if you have a lot of polyatomic ions, there's a lot of sort of multiplying in and keeping track of everything. So sometimes when you do have equations that have polyatomic ions, it's a lot easier to just keep them together. So for example, there's SO4 on that side, SO4 on this side, OH and OH, and really just sort of balance them as whole units. So for example, here, if I started with the sulfate, there's 3 sulfates on the left here, only 1 on the right. So I could fix it by putting a 3 in front of the sulfate on the right. That then changes my calcium to 3, which tells me where I should go next, which would be the calcium needs a 3. That also now gives me 6 of the hydroxides. So that tells me where I should go to the right and put a 2 here to give me 6 hydroxides. Also gives me 2 iron, so everything sort of falls into place. So you can go element by element, but it's a lot of keeping track of things. So sometimes it's a lot easier to kind of keep those guys together. We could kind of do the same approach on this one. We have a phosphate and a phosphate. We have a carbonate and a carbonate. In this case, 1 phosphate on each side, but we do have 3 carbonates on the right and only 1 on the left. So we could fix it by putting a 3. When we do that, that gives us 3 carbonates, but now gives us 6 of the lithiums. So to fix the lithium, we would go to the right and put a 2 in front of it. Gives us 6 lithiums and now 2 phosphates. So to fix the phosphate, we would put a 2 in front of it. And once again here, that drops the aluminum to what it needs. And it's just sort of a faster way of doing it. Obviously, you need the polyatomic ion looking the same on both sides in order to sort of do it that way. Any questions on that there? Okay, so now we've gone officially over balancing equations. Let us talk about electrolytes. So electrolytes are substances that are, when they dissolve in water, they basically will result in a solution that can conduct electricity. They're able to do that because, frankly, when they go for a swim, they produce ions. And it's the ions that are these charged guys that are flying around or swimming around, I guess, in the solution, helps sort of complete the circuit, help conduct electricity really well. So there's a few different types of electrolytes. There is a strong electrolyte, and a strong electrolyte will 100% break apart into ions. There's absolutely no of the whole units left. So if you took something like sodium chloride solution, even though we write it together in the solution, it is 100% broken apart into sodium ions and chloride ions. So 100% of what you have in there are the ions. There's absolutely none of those guys still in the solution. So if you had a solution of sodium chloride, basically that's all you got floating around are these ions in there. Because it creates a lot of ions, it's able to conduct electricity really, really well. Very common sort of experiment sometimes it's done is you take like a light bulb and you put some electrodes on it and you stick it into a solution. And if you did that for a strong electrolyte solution, the light bulb would go off very, very brightly. So it would conduct electricity really well. You would get like a bright light bulb. Different to that is a weak electrolyte. A weak electrolyte mainly stays together. But will produce some ions. So for example, if we took something like hydrofluoric acid, which is HF, it will break apart into H plus and F minus. But in solution, you mainly have this guy together. So that is mainly what you have is that HF unit still together. You do produce a little of these guys here. So again, if you looked at sort of a beaker that had HF in it, it mainly would be HF floating around in there. But you would have a little bit of H plus and a little bit of F minus floating around with it as well. But mainly it would be this HF still together, but a little bit of those ions basically being produced. So since it's able to really produce some ions still, it's still able to conduct electricity, but nowhere near what a strong electrolyte could do. So if you sort of did your light bulb example, you would have sort of a dim light bulb. It would turn on, but it would be very, very dim because there's just a few amount of ions sort of in the solution. One of the ways that you could recognize sort of a weak electrolyte is they are oftentimes written with two arrows headed in opposite directions. This is a reversible reaction. There's a forward direction that goes this way from reactants to products, and there is a reverse direction that heads in the opposite direction. So weak electrolytes usually have these arrows that head in both directions, and basically what happens is at some point they reach what is known as chemical equilibrium with each other. They kind of lock each other into place of how much we got on each side, and they go back and forth basically out the same direction. You do not see those arrows in a strong electrolyte. It is a one-way street. Pretty much everybody is dumping out into the product side and making those ions. And again, that's why I say a strong electrolyte and conducts electricity very, very well. Any questions on that there? Now, there's also non-electrolytes, which pretty much do not produce any ions. So they do dissolve, but do not produce any ions. So if you took something like sugar and you put it in some water, it would dissolve, But because sugar is basically carbons, hydrogens, and oxygens covalently bonded together, you will not produce any ions. And because you don't produce any ions, you will not conduct electricity. So it will not conduct electricity. Again, because of the lack of ions basically in that solution. So if you took like a light bulb and stuck it in a non-electrolyte, pretty much it would stay off. It wouldn't go on. Any questions on that there? Something like water, pure water, is it a good or bad conductor of electricity? Pure water is a bad conductor of electricity. There's no ions in it. Clearly the water that comes out of your shower and stuff is not pure water. They actually put ions in it to clean it and stuff like that. So you will electrocute yourself. It does conduct electricity because there's obviously ions in it. But if you have really just pure H2O, it has really no ions in it. And it's actually a bad conductor of electricity. But again, safety note, don't blow dry your hair in the shower tonight or anything like that, because you will get electrocuted. Obviously the water coming out of the tap is not pure water. So here's just an example of sort of the light bulbs there. Again, non-electrolyte, we won't see the light bulb go off. That's a weak electrolyte. You see a little bit of electricity being conducted, and then obviously a strong electrolyte will conduct electricity really well, and the light bulb will go off very, very strong. All right. So as we talked about, it is those ions that help conduct electricity. So most ionic compounds are pretty much strong electrolytes. So most ionic compounds, when they do go for a swim, will pretty much 100% break apart into the ions in solution. Weak electrolytes, this is another example of weak electrolyte is, this is acetic acid, basically vinegar. And again, in solution, it mainly stays here together, but will produce a little bit of these guys. And again, you see sort of the two-headed arrow there on the equation to indicate that. So it will conduct electricity, but not as strong as a strong electrolyte. A lot of weak acids are weak electrolytes. Weak bases as well are weak electrolytes. A lot of strong acids are strong electrolytes. Some strong acids are things like hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid. So these are a list of some really strong acids, and basically all those guys, when they go into solution, basically have broken completely apart. And that's really why they're strong acids, because as we talked about when we talked about naming acids, the cation is H+, and that's basically your definition of an acid, is the ability to produce H+. So any type of strong acid like hydrochloric acid, when it is in solution, will 100% break apart into H+ and Cl-. So in solution, it produces a lot of free H+, which is, again, is why it's considered a strong acid. As opposed to, say, this guy, which is acetic acid, still produces H+, but nowhere near the amount of something like HCl. But it still produces H+, which is why it's still considered an acid. But because it doesn't produce as much, it's considered a weak acid versus the guy up on top there that is a strong acid. Any questions on that there? By the way, as we come through this chapter here, we're going to talk about acid-base reactions. So those kind of list of strong acids is a good thing to sort of keep in mind of that they are strong. And if you plan on taking 200B, it's also a really good thing to keep in mind, because you'll see those a lot as well. So once again, a reversible reaction, forward direction and reverse direction, usually will indicate a weak electrolyte situation. And again, basically will stay together. Now, obviously, what happens when ions go into solution, especially where water is involved, because water is a polar molecule, there's a positive side and a negative side. It does surround the ions in solution, and that's what sort of keeps them apart from each other. There's a very strong attractive force between the positive ion and the negative ion, so the water almost acts like a buffer to kind of prevent them from coming back together. And basically, the positive ion is attracted to the negative side of water, which, as you hopefully know from our bonding conversation, is the oxygen side, right, is attracted to the positive ion, while it's actually the positive side of water is attracted to the negative ion, and the positive side of water is the hydrogen side. And again, they surround these guys, keep them from coming back together. This is also why people think perhaps sometimes, like when you dissolve something like sodium chloride or salt in water, that it's gone and some big chemical reaction happened. But it's still there. It's just surrounded by a ton of water, which we can't visually see the ions anymore, or the sodium or the chloride in there. And we know this is the case because, you know, if we do kind of like the experiments we did the other week, if you take something like this and you start evaporating it off, right, heating it up, all the water molecules will go into the gas phase, and that will allow those ions to come back together. And what you're left with is the solid that would be left over, like your sodium chloride. So kind of similar to what we saw when we were doing the empirical form on those evaporating dishes. You heated it up, all the liquid part went away, right? And you're able to see all the solid kind of stay together and stuff like that. So physical change actually when we make a solution and stuff like that. So non-electrolytes, again, are pretty much covalent compounds, which are not going to produce any ions, but they will dissolve. So here's a table, some strong electrolytes. You can see some strong acids over there. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. Those are strong bases. So if you look on the periodic table, right around where sodium, potassium is, hang a right to calcium, kind of come this way and this way. Any of those guys that have hydroxide in the formula are usually pretty strong bases, and they also will 100% break apart. So if you had something like sodium hydroxide, it is 100% going to break apart into sodium ions and hydroxide ions. And that is why it is considered a strong base, because the definition of a base is the ability to basically produce a lot of OH minus or OH minus. So something like sodium hydroxide can produce a lot of OH minus very, very quickly. Weak electrolytes, again, these are some weak acids. NH3 is actually a weak base. And that's a very common sort of weak base, which would be a weak electrolyte as well. And the way it works is it actually reacts with water, and it actually will produce NH4 plus and OH minus, and this is a reversible reaction. So once again, we'll produce a little bit of OH minus, which is why it's still considered a base, but it would produce nowhere near the amount of OH minus that something like sodium hydroxide would produce. Sodium hydroxide, once again, just needs to go for a swim and it will break apart. NH3 has got to go find some water, do a little bit of reaction, and produce a little bit of hydroxide, so it doesn't produce as much. And these are some non-electrolytes, again, carbons, hydrogens, oxygens, covalently bonded together. All right, so let's talk about why some of these things are important, and it is a type of reaction which is known as a precipitation reaction. And a precipitation reaction, I think we did an earlier experiment where you did all the guys together there in part B, and you look for cloudiness and that type of stuff to form. A precipitate is basically an insoluble solid that forms, and basically is also sometimes referred to as a PPT, is a abbreviation for precipitate. So if we have this reaction here, which is lead to nitrate, reacts with some sodium iodide to form lead to iodide, which is a solid, and sodium nitrate. This is a precipitation reaction because we have made a solid here, and that is what is known as a precipitation reaction. What we are looking at here is what is referred to as the molecular equation. We could actually write a couple of other types of equations that really describe sort of what is happening in this situation. We have some aqueous stuff over here. Aqueous are solutions, basically. And these are ionic compounds, which means they are pretty much going to be strong electrolytes. So really, when this thing is in solution, we could write an equation to help us understand what's really going on. And what would happen with this guy is it would break apart into its ions. So what we would have is lead that has a +2 charge that is floating around. We would also have a couple of nitrates. And that is basically what this guy would be in solution, basically floating around. The same thing would happen with this guy here. It is also ionic, it is also aqueous, it's a strong electrolyte, which means it would 100% break apart into ions, and we would get a couple of sodium ions plus a couple of iodide here. And we would distribute, obviously, the 2 to both of those guys. By the way, the 2 for this guy comes in front over here as well, in terms of when we break it apart. When this guy comes together on the other side, we do form the precipitate. And because it's a solid, it is not going to break apart. Obviously, it has come together, those ions, to make that solid, so it will stay together. So when we write this, we would keep the solid together. And typically when we write this type of equation, anything that is a solid stays together. Anything that is a pure liquid would stay together. Anything that is a gas would stay together. And anything that was a weak electrolyte would also stay together, because it will mainly stay together in solution. So those 4 things, if you come across it in one of these type of equations, solid, liquid, gas, or weak electrolyte, you should keep it together. You shouldn't break it apart into ions. That would leave us on the right-hand side our sodium nitrate, which is also an ionic compound, also a strong electrolyte, and will break apart in solution, and you would distribute that 2 as well. You would get a couple of sodium ions and a couple of nitrate ions. This type of equation, which really represents what is going on in this reaction, is what is sometimes referred to as the total ionic equation. Or sometimes people call it the complete ionic equation. It's basically the equation that sort of describes what's happening with all these guys in solutions. And again, once again, we keep together solid, liquid, gas, or anything that's a weak electrolyte. Any question on how we got there? When we have a total ionic equation, you should always be able to look on the left-hand side of the arrow and the right-hand side of the arrow and find ions that look exactly the same. So in this particular case, if we look on the left-hand side and we look on the right-hand side, we will see some nitrates, a couple of them here and a couple of them here. We will also see a couple of sodiums on the left-hand side and a couple of sodiums on the right-hand side. These ions that are the same on both sides of the equation, these are what are referred to as spectator ions. Spectator, if you are a spectator, you are pretty much just watching, right? And that is what these guys are doing. They're not involved in what is actually being made in this reaction. They're just there, frankly, to balance out charges. They're swimming around in the solution. They're just freely swimming, basically. What we do with the spectator ions in this type of reaction is, frankly, we cross them out and we get rid of them. And by the way, if you do this correctly, they should always completely cancel out. You should never have like 1 on one side and 2 on the other side. They should completely cancel out. If you find yourself at this point where they don't completely cancel out, it means you probably did not balance that equation correctly or did not carry a number down, but they should completely cancel out. And if we cancel them out, what we are left with is a third type of equation, which is known as the net ionic equation. And that in this case would be our lead 2 coming together with our iodide to form this yellow solid, which is our PbI2. And this is the net ionic equation. The net ionic equation pretty much gets right to the heart of the matter and tells you exactly what is happening in this reaction. What is actually happening, as you can see in the test tube, is we mix these 2 solutions together and we get a yellow solid that forms. And that yellow solid is made up of the lead 2 from the nitrate, lead 2 nitrate, and the iodide from the sodium iodide coming together. Question on any of those things? So molecular equation, total ionic equation, net ionic equation, and spectator ions. You always want to make sure all these are balanced so everything cancels out completely. And again, that starts with obviously the first one there. You want to make sure that guy is definitely balanced. Any questions on that there? Now, this type of reaction is a type of reaction which is known as a double displacement reaction. And in a double displacement reaction, it has a general form of AB plus B or CD. I'll learn the alphabet one of these days. Let's try that again here. There we go. That is CD. And how you can recognize this is these guys here will be two ionic compounds. So you'll have two ionic compounds on the left-hand side. And always in this situation, what will happen is the two positive guys basically will switch partners. And you'll make two new ionic compounds on the other side, AD and CB in this case. Now, in certain cases, like we just saw, one of these guys here will perhaps make a solid, which will give you what is known as a precipitation reaction. In one of these cases, maybe these guys make water, which is typically what happens in an acid-base reaction. So the double displacement reaction is the big category for which more specifically you could classify a reaction as a precipitation reaction or a acid-base reaction, and they're sort of subcategories of the big umbrella of double displacement reactions. Any questions on that there? And that is definitely what we see here. If we look at our original equation, this is lead 2 nitrate. That is a positive negative guy. That is sodium iodide, which is a positive negative guy. On the other side of the equation, the lead ended up with the negative guy, and the sodium ended up with the nitrate. And again, they just switched partners on the other side. So that is always a double displacement reaction. You could also more specifically classify, like we just saw there, as a precipitation reaction. And later on, you could classify some acid-base reactions as well. So there are multiple ways that you could classify reactions. And under the double displacement umbrella, these are the more specific ways you could classify that type of reaction. There's really three reasons why a reaction takes place. One is an electron transfer, which is the next type of reactions we'll talk about, which are redox reactions. Two is the formation of a solid, which is what we see here in a precipitation reaction. And three is the formation of water. Those are really the three reasons why reactions take place. Ultimately, all reactions could pretty much break down to one of these three situations happening, either electrons being transferred, waters being formed, or solids being formed. And that's really the basis of why all reactions sort of take place. Any questions on that there? Okay, so how do we know if a solid would form if we put two things together? And that is what is known as solubility. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent. It's basically if something is soluble, when we think about something being soluble, it means that pretty much everything will mix. And in terms of equations, we typically will give those guys the aqueous symbol. So the aqueous symbol means that they will mix, they'll make a solution. You would not get a solid form, so no solid being formed. If something is insoluble, based on sort of equations and stuff like that, those guys get the solid notation next to it, which means that, yes, we do get a solid formed in this case. So what helps us determine whether or not when we put two, say, ions together, will we get a solid or not a solid, is we look at what is known as solubility rules. So there are certain solubility rules that help us decide that when we put these guys together, and it works really nicely for double displacement reactions because basically we're putting ions together in these type of reactions, will we expect a solid to form or not? So let's take a look at some of these solubility rules here. These are compounds that are normally soluble. in water. So pretty much if you see any type of formula that has lithium, sodium, potassium, basically group 1, or you see a formula that has ammonium in it, NH4 plus, it is going to be soluble 100% of the time. On the right-hand side, there are no exceptions, which means that guy will always get the aqueous symbol next to it. You would not expect a solid to be formed. If you have something that has nitrate in it or acetate, which is the second guy there, and you see it in a formula, it also has no exceptions, which means 100% of the time, we would expect everybody to be aqueous. You don't even have to look any further than seeing those guys. If you have somebody that has chloride, bromide, or iodide in that solution or formula, they are going to be soluble in most situations. But there are 3 exceptions. This is silver. That is mercury 1, by the way. The one with all the 2s is mercury 1. And that is lead 2. So in most situations, if you have chloride, bromide, or iodide, it will be aqueous. The exception would be if silver, mercury 1, or lead is part of it, then it would go from being aqueous to being a solid. So that would be the opposite would occur on that situation. Sulfates are also going to be soluble in everybody, except for silver, calcium, strontium, barium, or lead. So if you have any of those guys together with sulfate, they will be the opposite of that and will be actually a solid would form. So for example, if you put barium sulfate together, you would expect a white solid basically to form. If you put sodium sulfate, you would expect it to be aqueous and be a solution. So anything that has the aqueous is basically going to be a solution, like all the solutions we've used before in the bottles. Anything that's obviously a solid would form a solid. Any question on those rules there? Now, there are certain things that are typically insoluble in water. So these are guys that normally will be insoluble and make a solid. So things that contain hydroxide will normally be solid unless it's one of these exceptions, which are the same exceptions we talked about on the previous slide, basically group 1 or ammonia, then they will be aqueous. There's also some here that are slightly soluble, and for the most part, people consider slightly soluble to be more leaning towards insoluble, so being more leaning towards being on the insoluble side. Anything with sulfide, which you never want to be around because it smells, will also be typically solid in most situations. There are, again, the same exceptions. Group 1 and ammonia will make it aqueous. And then obviously these guys as well, calcium, strontium, or barium. And then things that have carbonate or phosphate in it will once again be typically solids, except once again, these are group 1 and ammonia, which would make them aqueous if they're on this side. So really most of the exceptions here are basically the soluble guy on the other side, which was group 1 and ammonium. So once again, if you see a group 1 or ammonium, regardless of what it's attached to, it's going to be soluble. Any question on those rules there? So if we look at these guys, we want to determine the solubility. So let's take a look at this one. This is potassium hydroxide. And frankly, you may not be able to find both things on the chart, or maybe you will. But once I go to here, which is potassium, that is group 1. And frankly, there's no exceptions for group 1. They're always going to be soluble. You don't have to go any further than that. So this is going to be soluble, aqueous, because K is group 1. Here we look at silver, which we may not find on the big category, but we can find bromides. And bromides are soluble in everything except for silver, mercury, and lead. And in this case, obviously, silver is there. So instead of being soluble, this would actually be insoluble because of that. And you would give it a solid notation. Any question on those two? We look here at calcium and we look at chloride. So once again, if we kind of go backwards here, this is chloride, which is soluble in everything except for silver, mercury, or lead, which is not the case in this case. So we would expect this guy to be soluble again because it is not attached to one of the exceptions. Lead to nitrate, frankly, as soon as I see nitrate, if you look on that table, nitrate is soluble in everything. There's no exception. So we would expect this to be soluble because of the nitrate. It's soluble in everything. And lastly here, this is our lead 2 sulfate. So if we go back to our table, we find that sulfate is soluble, except if it happens to be attached to lead in this case. So because it's attached to lead, it would actually be the opposite, and it would be insoluble in this case. So this is how we could use solubility rules to help us determine if we kind of combo a couple of things together, would we get something that would make a solid, or would it be something that is aqueous? Any questions on how to use solubility rules here? So let's take a look and see how we can kind of put these together with the reactions and stuff that we were talking about. Let's say we had this equation here, and we wanted to write our three equations. We want to write the net ionic equation for silver nitrate and sodium chloride coming together. So if we were to do this, we would take our silver nitrate, which would look something like this. We would react it with our sodium chloride, which looks something like this. Now, if you were not sure what is going on here in terms of what type of reaction, you should hopefully know that silver and nitrate are ions. So that is a positive guy and a negative guy. And sodium chloride is also an ionic compound, which means that's a positive guy and that's a negative guy. And that should scream to you that this is a double displacement reaction, which means on the right-hand side, what's going to happen is the silver is going to go hook up with the chloride, and the sodium is going to go hook up with the nitrate. So this is the right-hand side of the equation, which we definitely want to make sure that we get the correct formula down. So the basic unit of silver is silver that has a +1 charge, and chloride has a -1 charge, which means when we put them together, we just need one of each of those, +1, -1. Sodium is +1. Nitrate's a polyatomic ion that is -1. So once again, when we put those guys together, we just need one of each of them. So it's really important to make sure, as we were talking about earlier, that we get the correct formulas down first. Any questions on that there? We also want to make sure it's balanced, right? So if we take a look on the left-hand side there, we got one silver, that's good. We got one nitrate, one sodium, and one chloride, so it actually is balanced in this case. A reminder, it won't always be balanced, so you do want to make sure that you do check it. First off, any questions on how I got to that equation? Now that we have our ionic equations here and our ionic compounds, we can figure out the solubility by using our solubility rules. So I look at the first one, which is silver nitrate. As soon as I see nitrate, it is soluble in everything, which means it would get the aqueous symbol next to it. I look at the next one, which is sodium chloride. Sodium is pretty much as far as I need to go. It is group 1, which means it's going to be soluble in everything. So I could safely put the aqueous symbol next to that. I could also look at chloride, which is soluble in everything except for silver, lead, or mercury, which is not the case here. So I could actually look at either one in that particular case. They both tell me that it should be soluble. Going to the right-hand side, I could look at chloride, which is soluble in everything except silver, lead, and mercury. And in this case, this chloride is actually attached to silver. So instead of being soluble, this is actually going to be a solid here in this case. Lastly, here I can look at sodium on those solubility rules, and that's pretty much as far as I need to go. It is going to be soluble in everything. It would get the aqueous symbol. Or I could even look at nitrate, which is also soluble in anything, and figure it out. Any questions on how I figured out the solubility there by using those rules? This also tells me, as I can see, this is a double displacement reaction, which, as I mentioned, is the big umbrella. But more specifically, we formed a solid, which means this is also a precipitation reaction, yeah? So again, a precipitation reaction is a more specific classification of a double displacement reaction in this case. What we have up here we'll get rid of the arrows here to clean it up a little bit, is what is known again as the molecular equation. So this is the balanced molecular equation. We once again can break everybody apart into the total ionic equation. And if we do that, our silver nitrate would break apart into a silver ion floating around, plus a nitrate ion. And again, that is basically what is happening with silver nitrate. It is a strong electrolyte going to break apart. Our sodium chloride will do the same. We'll have a sodium ion and a chloride ion, as it is a strong electrolyte and will break apart. Should I break apart the silver chloride? I should not, because it is a solid, so it will stay together. The sodium nitrate is a strong electrolyte, so it will break apart into a sodium ion and a nitrate ion here. Squeeze it in here. This is the total ionic equation, our complete ionic equation. This is really representing what is floating around in that beaker or wherever you poured these two things together is basically what that represents there. I could look on the left-hand side and the right-hand side here of this arrow, and I can find my spectator ions. And in this case, my spectator ions are my nitrate on both sides, looks exactly the same. And my sodium on both sides look exactly the same. These guys here would be our spectator ions. So once again here, we can get rid of our spectator ions, as they should completely cancel out. And that is going to leave us our net ionic equation. What is really happening here is the silver ion that's coming from the silver nitrate is going to go find the chloride ion that's coming from the sodium chloride, and they're going to come together to make this white solid that you would get, which is the silver chloride. And this would be our net ionic equation. Any questions on that there? So our net ionic equation, again, really represents, what is truly happening, what the real reaction is. It is this precipitate that's being formed. And as I mentioned earlier, that is really one of the reasons why a reaction happens, is basically a precipitate being happening here. So overall, big classification of this type of reaction, double displacement. More specific classification of this type of reaction is a precipitation reaction. You could, if you needed just a net ionic equation, go backwards if you know what the solid is and know how that breaks apart into its correct ions. You could take that and go, okay, that's a silver ion and a chloride ion. And you could actually get the net ionic equation pretty quickly that way as well. Any questions on how to write molecular equations, total ionic equations, net ionic equations, how to figure out spectator ions, or to use solubility rules here to help you do so? Any questions on any of that? Okay.